Hello everyone. So welcome back to the video lectures on image and speech processing techniques. So in the last class we have talked about the image enhancement techniques that were available. So we have talked about histogram, we have talked about histogram equalization, right? If we want the histogram to be applied locally, so how do we use the local histograms, right? So we have talked about these concepts. In the before video lectures we have talked about intensity transforms, right? So in today's video's lecture, we will be talking about on the problems that are available for image enhancement techniques, right? So let's go for the first problem, right? So this is like we have an image which is given by a matrix, right? And it is given by of this form 66776, right? So if you observe here, it is a 5 cross 5 image. So totally we will have 25 number of pixels. So the question is, we have to perform the histogram equalization on it, and we have to plot the histogram plots of both input as well as the output image. So the first thing that we have to do when we have such kind of a question is, we have to just draw, or just we have to create a table which is having the possible intensity values that is existing in the image or in the given problem, and the count. We have to do our count. How many number of pixels are having such same intensity value. So this is basically equal to your unnormalized. This is your unnormalized histogram. So we have the unnormalized histogram. So let's start off here. So we have the possible intensity values to be 6, 7, right? Then 5, then we have 2, then we have 3, then we have 4, then 3, 3, 4, 5, right? So we have noted down all the possible number of intensity values. So let me write down in the form of in a systematic way. So this is 2, 3, 4, 5, 6, 7, right? So how many pixel values are having the intensity value to? Let's count them out. 1, 2, 3, right? So we have 3, whereas the intensity value 3 is 1, 2, 3, 4. The intensity value 4 is 1, 2, 3, 4, right? So next we have 5, which is 1, 2, 3, 4, 5. Next we have 6, 1, 2, 3, 4, 5. And 7, 1, 2, 3, 4. Right? So we are left out with 4. So what will be the total? It will be total 25. Right? So this is right. So we have total number of 25. So we will have the total count to be 25. Now this is my unnormalized histogram. Now we have to calculate my normalized histogram, right? How do we do this? Normalized histogram we have to calculate. So how do we do that is the count by the total number of pixels. So that is equal to 3 by 25, 4 by 25, 4 by 25, 5 by 25, 5 by 25, 4 by 25. So this is my probability, as well as it is the other term called as the normalized histogram, right? So now how do I do it? I plot my input histogram, which is given by the R value, right, on my x-axis, which is the intensity values 2, 3, 4, 5, 6, 7, 8, and I have on my y-axis I have my probability, right? So here I have intensity 0, 1, 2, 3, 4, 5, 6, 7, right? So this I have here 3 by 25. So let me just mark here 1 by 25, 2 by 25, 3 by 25, 4 by 25, 5 by 25. So this is the probability values. So if we are plotting it, how do we get it as 2, 3, right? Next we have the intensity value 3, that is equal to 4 by 25. This is again 4 by 25. This 5 is 5 by 25, 6 is 5 by 25, 7 is again 4 by 25. So this is my input histogram, right? So this is my input histogram where I am plotting on my y-axis to be the normalized histogram or my probability of my intensity values. On my x-axis I have my intensity values. So this kind of a plot is my input histogram, right? So let me just continue here. So I have the intensity values 2, 3, 4, 5, 6, 7, and the normalized histograms are 3 by 25, 4 by 25, 4 by 25, right? 5 by 25, 5 by 25, and again I have 4 by 25. So this is my input histogram, right? So we have plotted now. This is my R, okay? This is my probability of R, RK, right? This is my input histogram. So how do we do my output histogram? We have to calculate the value of S. So what is my S? How do I get my S? I get my S is equal to probability summation of probability RK into the this is equal to L minus 1 into probability of summation of the probability of RK, right? If I want. Now, how do I do that? I do it step by step. Now, what is the L here? L, first step is we have to calculate, when we want to calculate the output intensity values, we have to know what is the L value here. Since in our question, nowhere it is specified what is the value of L, right? So what do we do is, what is the maximum value that is available for our in the image segment? It is 7. So how many bits do we require? We require how many bits do we require to represent the intensity value? 7 is 3 bits, right? So we assume that this image is a 3-bit image. So when it is a 3-bit image, L is equal to 2 power 3, which is equal to 8. So we say that 8 minus 1, right? Into, if we are calculating for S naught, which is R naught is this, R1 is this, R2 is this, R3 is this, R4 is this, R5 is this, then R naught is equal to 8 minus 1 into probability of R naught, right? So this is 7 into probability of this is 3 by 25. So that we get to be 21 by 25. Then S1, if I am calculating for S1, then it is 8 minus 1 summation of probability of R ranging from 0 to K, whichever K value we are calculating. So it is 1 means R K. So this is equal to 7 into probability of R naught plus 7 into probability of R1. So that is equal to 7 into 3 by 25 plus 4 by 25. So that is equal to 49 by 25. So this is equal to 49 by 25. This is again equal to what do we get? 7 into 3 by 25 plus 4 by 25 plus again 4 by 25. So this is equal to 8 plus 3, 11. 11 into 7, this is 77 by 25. So 77 by 25. Then again we go on for my 5 by 25 plus 3 by 25, my previous value, right? So 5 by 27 into 5 by 25 by 77 by 25. So that is equal to 11 by 111 by 25. Okay. Now after this, how do we get 7 by 25? 7 into 5 by 25 plus 112 by 25. So that is equal to 7 into 5. This is 35. So 112 plus 35 is 147 by 25. Next is your 147 plus 7 into 4. This is 28 by 25. So what do we get? we get this value to be, say, 175 by 25. So this is my output intensity values, right? So we have now have to count the values which are having the same intensity values of 49. So what will be the count now again here? It will be 3. The count will be 3. Same here again, it is 4, 4, 5, 5 and 4. The count is not changing. So the output probability will now not change from 25 by 25, so on. So we are plotting now S0 value with respect to their probability. This will give me my probability output histogram value. Right? So basically what did we do from here is, we have the image. Right? So the first step, when we have an image, we have to find out, for histogram calculation, we have to find out what is the number of possible intensity values, what is their count, and what is L, right, for calculating my output histogram. So from here, I have, from this image, we have taken out what are the possible intensity values that we are having. Then based on this image segment, which is a small segment of the image, we have counted the number of pixels which are having the same value, which is equal to my unnormalized histogram. From there, we have converted into a normalized histogram by dividing it by the count by the total number of pixels, which is equal to 25 in this case, because we have a 5x5 image. Then we are plotting the R value on my x-axis, and the y-axis we are taking the normalized histogram, we are plotting it. Based on that, we have calculated, or we have plotted by input histogram. Right? So after this, we are going for my output histogram. There we are calculating, the first step is we have to calculate the output intensity values, right? So which is mapped from R to S. So how do we do that? We do it using this formula, right? L minus 1 into sigma of probability of R into Rk, right? So from this we have obtained my S0. From there we have counted what are the possible output intensity values we have got in this way. Then from there we have counted how many number of pixels are having the same intensity output values. From there we have plotted the output histogram, output probabilities, so that we are plotting S0, which is given by this column, and S probability we are calculating. So this is giving us the output histogram, right? Now let's go to the next problem. Right? So here we are being given a symbol combination of 6 symbols A, B, C, D, E, F, and the source frequencies are directly given here. So we have been given the possible intensity values and the count. Right? So we have here A, B, C, D, E, F, and we have the count to be 45, 13, 12, 16, 9, 5. So the total here is 100. Right? So the input histogram, if you want to calculate, how do we do? 45 by 100, right? 13 by 100, 12 by 100, 16 by 100, then 9 by 100, 5 by 100. So this is my input histogram, right, which is my normalized histogram or the probability. So how do we plot here input histogram? If you are plotting, this is R, this is the input probability, right? So we have plotted this to be A, B, C, D, E, F. Okay, now we plot the histogram. So this is my, which is probability. So from there we have got my input histogram, right? After this we have to get our S0 value. We have to get my S0 or S values from my input histogram. So this is equal to R0 equal to this, R1 equal to this, R2 equal to this, R3 is equal to D, R4 is equal to E, R5 is equal to F. Right? So now how do we calculate? Which is equal to L minus 1 into sigma of probability. Right? So that is equal to, here here we have 6 symbols which is equal to A, B, C, D, F, right? So these are the symbols. We don't know what is the maximum value that is available. So in that cases, we take a 8-bit image, right? So that means we are considering the image to be a gray image. So L is equal to 2 power 8, which is equal to 256, right? So this will be equal to 255 into probability of this value. So this is equal to 255 into 45 by 100, then 255 into 13 by 100, 12 into 255 into 12 by 100, then 16 into 255 by 100, then 9 into 255 by 100, then 5 into 255 by 100. So this is my output intensity values. Then I count the probability values which are having the same intensity values. Based on that, I will count the values which are having the same intensity values. From there again, I will calculate my probability that I will plot here. So this is with respect to S, and this is equal to my probability of SK. So this is equal to my probability of SK. So this will give you my probability, or this will give you my output histogram, right? So similarly, we have this problem here. So here, if we consider here directly, we have been given the intensity distributions 0, 1, 2, 3, 4, 5, 6, and the NK values are given, which is having the probabilities of 0 point. So directly, if we are plotting the histogram, so how do we do it here? Which is equal to R. I'm taking my y-axis probability, right? So this is equal to 0, 1, 2, 3, 4, 5, 6, 7. So this is my 7. So from here I have 0.19, 0.25, 0.21, 0.16, then 0.08, 0.06, 0.03, 0.2. So this is my input histogram. So we see that it is not a equalized form. So from there we are going to calculate my S values. So how do we calculate my S values? Is equal to L minus 1 into sigma. So here we have, it is a 7. So we are taking 2 power 3, which is equal to 2 power 3 minus 1, which is equal to 7. 7 into sigma of probability. So this is equal to 7 into 0 0.19, which is equal to S value here. So this is equal to 7 into 0 0.19, 7 into 0 0.25, 7 into 0 0.21. Okay, so on and so forth. Based on that, we will get my output histogram. Okay, next kind of a problem is if we have a 4-bit image of this form. Okay, now we have to calculate all the bit planes that are available for this. So this is the bit plane slicing concept. So this is equal to the bit plane slicing concept which we have read there. So there what we have seen that is it is a bit plane slicing. There every intensity value will be represented in the form of a bits. Then each bit, okay, say if it is we are considering the MSB bits, then MSB bits of all the intensity values are combined together and we form a bit plane which we are calling it to be the MSB bit plane. So based on that we can create multiple bit planes. And each operation that we are doing, like image enhancement we are doing, then we have observed that the first 3, the MSB bits or the next highest bit or the next highest bit, these 3 bits when combined together are having most of the information of the image, whereas the later lesser number of bits are having the least information. They are useful for differentiating the fine details. So overall image actual information is contained in the MSB bits and the higher bits. So here we are seeing that if an image is being represented by 4 bits, then we call the image to be a 4-bit. So here it means the image intensity values, each intensity values are represented by 4 bits. So how do we do it? 4 bits means the same image I, say assume I, can now be represented as 0 0 0 0 0 0 0 1 1 0 1 0 0 0. Okay, then we have 1 0 1 1. Then we have 0 0 1 0 0 0 1 0 0 0 0 1 0 0 0 1. Then we have 0 0 0 1. Then we have 15. How do we represent 15? So 15 is represented as this is 2 power 0, 2 power 1, 2 power square, 2 cube, right? So how do we represent it as 12 is 2, right? So this is equal to 14, 8 plus 4, right? So this is all ones, this is this. Now we have then we have 6. How is 6 represented? 1 1 0. How is 9 represented? 1 1 1. Then 0 1 1 0. Okay. 9 is represented as 10 is represented to be this, right? So we have this having the same image I can be represented in this form where each pixels or peaks each pixel values are represented by 4 bits. So now if we want to find all the bit planes, then we will have the MSB bit which will have only the MSB values of all the intensity values, which is equal to 0 0 0 1 0 0 0 0 0 0 1 1 1, then 0 0 1 1. So we have the MSB bit plane. Next we will have the next bit plane which is equal to, which is having the next highest bit 0 0 0 1 0 0 0 0 0 1 1 0 1. Next row will have 0 1 0 0. So this is the next highest number of bit. This is the MSB bit plane. This is the second highest bit plane. Next highest bit plane will be equal to 0 0 0 1. Next we have next row will have 1 1 0 0. Next is 0 1 1 0. Next we have 1 1 0 1. So this is the next bit plane we have. After that we have the LSB bit plane which is equal to 0 1 0 0 0 0 1 1 1 1 0 0 1 0 1 0. So this is my LSB bit bit plane. This is my MSB bit plane, whereas these two are my the other bit planes. So this division of my bit or my intensity values into bit planes is called as my bit plane slicing. So this is very useful when we go for image compression models. So we have the RLC coding as well as bit plane coding. So there what we will do, we'll apply the RLC coding on each bit plane. Okay, so we can compress the image on each bit, and this whole by combining all the compressions of each bit planes, then we can compress the whole image. So this bit plane slicing is very important when we are going for image compressions, as well as when we have less number of storage, we can differentiate where the actual information is stored there. So based on my MSB data and the highest number of bits, which is equal to highest number of bits, which is this and this. Sorry. These three bit planes can be used for reconstruction of my image. The LSB bits usually has the least data, and it is used for differentiating the fine details. So actual overall image can be obtained using my MSB bits and the highest two bits. Right. So this is the next probable question in my image enhancement. Right. So next here we have a question saying that if you assume that continuous intensity values are there, right, and the intensity values of the image have the probability density function of this form which is equal to 2r by L minus 1 whole square, right, and we are having this condition that if it is between 0 to L minus 1, then the probability of this is equal to 2R by L minus 1. If the probability is equal to 0, if the R is falling in other than this range. Now what we are doing is we are trying to find the histogram equalized image for that, which is equal to the S probability, S plausible intensity values. For that we are trying to calculate my probability density function, right? So how did we do that? We have said that. So how can we do this? If this is equal to probability of R, which is equal to 2R of L minus 1 whole square, right? So what are we trying to do is, we are trying to calculate my S value, which is equal to, first we have to calculate the probability of my S, that is equal to dr by ds into probability of my R, right? So we have to calculate my dr by ds, right? So how do you calculate it? From there we have said that S is equal to L minus 1 into integration of 0 to R probability of R d w, right? So here we have L minus 1 into 0 to L minus 1, which is equal to probability, which is equal to 2R by L minus 1 whole square dw, right? So let's do like maybe dw. So this is equal to L minus 1 into 2W by L minus 1. So that L minus 1 I'm taking out. So we have 2W integrated over 0 to L minus 1. So I have W square, right? Where the values are ranging from 0 to L minus 1. Right? So from here, what do I get? L minus 1 into L minus 1 whole square minus 0 by L minus 1 whole square. So I get my probability density value, S value, to be L minus 1. Right? So from this, I can calculate my dr by ds. From there, I can calculate my probability density function to be, which is equal to L minus 1 into 2R by L minus 1 whole square, right? So from this I get that, I get it to be 2 by L minus 1 whole square. So this is equal to my probability density function of my output function, which is equal to 2 by L minus 1, which is equal to my output density function, output probability density function. So this is a equation of my histogram equalized image, the density function, and from this we can see that it is a form of a uniform probability density function distribution function. So we can say that the histogram has been equalized, right? Similarly, we can see the further questions in the digital image processing questions, processing image, where it is defined by Gonzalez book. So this is a good book where you can find various number of problems, and mostly they can be divided in these problems ranges where we have studied right now. Right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.